purely like kind of data intuition section, but then I just saw how much I think it really affects like the analysis going forward. Okay, so this is a quote that I pulled out from a book. So most of the egregious statistical assertions are caused by good statistical methods applied to bad samples, not the opposite. Some of the most egregious statistical mistakes involves lying with data. The statistical analysis is fine, but the data itself is bogus. All right, and you'll see this just all the time that like it's very easy to you learn in school, right, these different statistical methods and correlation coefficient and p-values and things like that, but the problem is always already fraught before that even occurs, because the collection of the data was poor and the data was missing. So the first step that you do is basically define a population of what you're trying to study and what you're trying to make conclusions about. So this might seem again like kind of academic, but if you think about it in in like a business setting, it'll be like, well, users. But are users really your population, or is it active users? Or maybe you care about users who are falling off or at risk of falling off, and what do they look like? If you talk about like potential users, what is that what is that population? So it's like by population we mean the actual individuals, and it says like beyond the range of the data, right? Even beyond the people that we're able to collect, right? Who are the individuals? So for instance, right, for the elections coming up, it's voting age individuals, or is it, right? Is it people eligible to vote, or people who are likely to vote, people who will be voting, right? It probably actually is the people who will be voting. And then what you try to do is match that population by collecting data from it. So the first step, right, is defining the population. And then, just to kind of emphasize this came from a medical journal, right? A physician might try to find out, like, what is the average blood pressure of Englishmen aged 40 to 59? But who are the Englishmen? Because not all Englishmen live in England, right? And then, and how old are the patients? What sex are they? Where do they live, etc. So, this point I think of like not all Englishmen live in England. It also gets to, you just have to think about like, what is the point of collecting this data, right? Is the point to draw some conclusion about kind of like the English medical system and how that combines with English people, or is it more about like the genetic characteristics or whatever of English people, or just like legacy of where they lived, regardless of where they live now, right? So it's like this gets to kind of population is tied to like what conclusion are you thinking of drawing from the data. While I was writing the lesson, this was like years ago. This came out in 60 Minutes. Leslie Stahl asks, if I walked into a lab anywhere in the country doing animal research, what are my chances of coming upon a study with only male animals? Very large. Today, like this was like 3 years ago. Yes. But turns out like female rats might be important to study too. So this person, says, so to control, most researchers are just studying males, and I was also just studying males. And she's like, well, were you doing that because it made sense for the study, or you just didn't think about it? And the researcher's like, I just didn't even think about it. So it's not the point. It has nothing to do with this researcher, right? This was happening, like she says, this is happening everywhere. So, thinking about the population and then thinking about we'll talk about like how the data set matches the population or likely does not match the population is extremely important. It's one of the reasons why you see me keep going back to that. Remember like the alcohol revenue data set in Texas? Like, why is that such an interesting data set to me? Well, because they're legally mandated to report on it. Now, again, that doesn't mean that everybody is reporting on it. So it's something still to check. But that's one way, like one of the reasons why I find that data set interesting is because it's more complete, or at least it should be. So, okay, and then the other thing to be careful about is just units of measurement. This may feel weird to put in right here, but if you think about like a CSV file and gathering that data, You have to think about what are the rows of the data. So let me see. Okay, here, this is like kind of an interesting example. So let's say we get a data set of NBA players, right? Players that play basketball and their statistics. And then we see this, we try to gather statistics. So we see, the games played. And then the game here has the game started, right? And then it has kind of like how many 2-pointers they made. Here are the units of measurement. Like it depends on how you're trying to make conclusions about the data. But if you're trying to see like, well, how many 2-pointers do they make? The unit of measurement, at least the smallest one that I see, is the games played, right? But that doesn't actually get to, maybe how often are they taking 2-pointers. For that, maybe you need like minutes played or even down to the seconds played, right? If you're trying to draw like effectiveness, right? Like in other words, like their percentage, like their 3-point percentage or their 2-point percentage. Well, one question is, are they playing in games that matter, or moments that matter? So that's why, like in the NBA, like people have like crunch time statistics, meaning the last, I forget what it is, like 3 or 5 minutes of a game that's relatively close. That's called like crunch time, right? Because those points, that really can swing the difference of a game. Because if you're just, getting points in moments that don't matter or where it's a blowout, it may be a lot easier, right? And a lot easier to pad your stats. So here it's like, the reason why I bring this up is, when you just read in a data set and, you can look at the completeness, but then also what does each row represent? Because it's not every minute of every game that this person is playing, right? And we're going to see this kind of problem with grouping the data, which is inevitable, come up again and again. So whenever you kind of see a data set, one thing to identify is just, what we call like, oftentimes people call the grain of the data. I also just like to think by the grain of the data, it is what does each row represent, And then another thing to consider is just like the dimensions, meaning, what is like how can we kind of group the data? Here it's a little harder to see. There's not too many ways to group it. I guess you can, think about the season, if there's various seasons, or group the team, right? Group by the team. But again, like a lot can go wrong with grouping the data. Did this person play on the team the entire time, for an example, or things like that. But yeah, like here, even though it may not seem that there's a grouping, there is, because every time we do this kind of like points, if we're trying to draw some sort of conclusion about the data, like how many points did they score? Well, points per what? Points per game, points per minute, points total, points per career. Like all that grouping has just like different implications. Let me see. Question. Is this something a DE will discuss commonly with a data scientist, data analyst, to come up with a common ground regarding the population? Or is it solely the responsibility of the data engineer to identify the correct population? Okay, this is an interesting question. So, Conwell's like, well, whose role is this? And there's a couple of things I would say. So ideally, it would be probably the data scientist. One thing to note is that, because, if you think about it, you'll see this when we do like internship stuff, but like people will ask you to do data analysis work. Why? Because you have your hands on the data, you're, facile with it, you have, this engineering skill set. So more and more data engineers, it's kind of like what I was saying before, data engineers are asked to do more and more data science work. So there may not be like a data scientist, especially one that's coming from like a statistical background, on the team. It may rather just be like, okay, you work with data, so they ask the data engineer to do this. The other thing I'd say is, even if you have a data scientist on the team, that doesn't mean that they're necessarily asking these kinds of questions, right? It's very easy to like ace your exams, or not easy, but actually it's not as hard as you would think, to like ace your exams in your like Masters of Data Science without thinking about these kinds of questions, right? Like, Why? Because oftentimes we're not assessing for it. It like feels a little more like soft, right? There's no math involved here, but it's still, it can change everything in terms of actually drawing conclusions about this. It honestly feels more like my law background than like a data science background. You're basically, in a way, you're playing like devil's advocate, and I'm trying to show some, like, the point of these lessons is to show some like very common ways that things can go wrong, you know. So like defining the population is the first step, because this is the ideal, right, of what we're trying to measure, and putting some care into that, right? Like, are you thinking about, an individual? Are you thinking about a town, right? The health of a town, the health of a family, right? Every time you deal with like a group, you go into a group, which happens all the time, right? You kind of you have to be very careful about that. And then, of course, like, is what you're measuring, is what you're studying, the data set you're working with, does that reflect the underlying population that you're trying to draw conclusions about? Okay. So the next thing, um, is, how do you kind of get this data? Like, when you get a data set, how does that, like, where is that data set coming from? So again, kind of like we said, the first thing is we typically define a population, right, that the study is based on. I don't know why. Oh, select a sample. Okay. And then the ideal is, or not the ideal, actually this is the ideal. The ideal is a simple random sample. So simple random sample is, you have this underlying population, say it's, U.S. voters, people who will be voting in the election, right? And then you randomly select them. This way you don't have to call everyone and ask them, right? But you get a subset of them that, and if every person in the population, meaning all people who will be voting, have an equal chance of being selected, then this should be predictive, right? If they're telling the truth, if they don't change their mind, right? And even if we just call 50 people, if every person, or really like 100 should be enough, that if every person has an equal chance of being selected, you'll essentially be fine. There's this problem of variance, but typically like around 100 people, even you'll see in like Gallup polls, they only try to hit 1,000. You'll be okay. But the problem goes with that, it's basically impossible to get a simple random sample, meaning it's impossible to find a selection technique where every person has an equal chance of being selected, and then you ask them. Okay, so as we said, the first step is defining the population. We said, we have to consider the unit of analysis, right? That goes back to that grouping problem, meaning, are you talking about students, classrooms, schools? If, say, you're trying to see, I don't know, the physical fitness level or the health of, say, like a student body or something like that. Okay, this is important, right? The sampling frame, this is, let's say you're trying to poll U.S. voters. How do you actually, like, what is the resource that you're using to call them, email them, talk to them, to find, to get information from these U.S. voters? It's a very hard thing to do. So, like you hear about this in academic studies, it's like less times they're using college-age students, especially for like psychological studies and things like that, right? Like it's just like college-age students, and it's hard to obviously draw conclusions about the broader population from this. So, you could use like electoral register, a phone directory, homeowner list. Why is this appropriate in a data engineering course? Well, this is all about where are you getting your data set from, basically, where is this information actually coming from, and what is the importance of going after and finding a higher quality data set that is more likely to represent, right, the underlying population. Okay, so hopefully this tells you how to evaluate the quality of the data and consider where is it coming from. Okay, so let's say we then use a phone book, and then we call everyone, or call 1 out of 100 people in the phone book. So then the next step is to seek responses, right? So you call these individuals, or you email them, or you knock on their door and try to collect information about them. Then finally, we have a researcher record this, or we have someone like self-report. Okay, so there's a lot of issues here with the seek responses and enrollment because, right, as you'll see, we'll get into biases, but basically something can go wrong at every single step here, maybe except for random selection. But in choosing the sampling frame, right, like, are you choosing, even if you choose a phone book, you may have unlisted numbers. If you choose a register, electoral register, new people are going to sign up to vote, right? For seeking responses and enrollment, what time of day are you calling people? Of course, lots of people are not going to want to pick up their phone. People have cell phones, right? Things like that. So there's always issues. So this is kind of the example I give, right? About with each stage here to think about where things can go wrong, and they always do. So these are things that, like, in a take home or whatever, you want to, you want to raise these issues and at least like put them as bullet points as things that can go wrong. Oftentimes what people will do is take a stratified random sampling. So what this means, for example, right, in elections, what they'll do is they'll look at the past election and then they'll see what is the breakdown of voters, right? How do they do that? There are people that stand 30 feet away from an election booth, and then when people go back to the parking lot, they ask them, 100 different pieces of information and then give them, $15 or whatever, right? So then the next election, they try to see, okay, these are the percentage of people of this income level, of this, race, of this, in this county, of this occupation, blah, 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 right? That voted in the last election. Let's try to match that in this new election, right? So when we go and poll people and we get this percentage of, let's say, like Hispanic people, well, we're going to then say, well, there was 10% of Hispanic people who voted in the last election, and so they try to, multiply by a certain extent that it matches that, now, even if I was only able to get, 2% of my of the people answering my poll were Hispanic, I multiply that by 5 to get that to the population, the expected voters in the next election. The problem with this is that being Hispanic is not necessarily predictive of how you're going to vote, of course, right? So maybe it was in the last election, but is not in the upcoming one. Right, you heard a lot of in the 2016 election that one of the most predictive aspects was whether someone attended college, right? Not their income, not their race, blah, blah, but rather just, whether they attended college, which was a new factor or a more important factor in the previous election. So this is the issue, is that people don't, I'll go into here, is that even if you do stratified random sampling, the presumption is that this strata, right, the groups that you're dividing into, are predictive, but they're not always, right? And the emphasis that you're putting on them can change all the time. So this guy in this book, he goes, the problem with stratified random sampling is that it relies on this image of a microcosmic population, that a cleverly selected sample is an exact replica of the larger universe. It's the Noah's Ark sort of conception, with proportional representation of different types of individuals. And this is the point I was just making. If we knew exactly what measurable attributes were most predictive, we might try to design proportionalized representation. We might try to design proportionalized samples only on those attributes, but we don't know that information, right? If we knew what attributes were going to be predictive, cool. Then we can just select, this percentage of people from each race. But then it turns out that doesn't matter, right? So, like, the strata that you're breaking these groups up into and then multiplying by is off. Right, so people still do this. They obviously because they don't have it's hard to come up with a better technique. But it's still going to be important to try to see how this is changing from time to time and how predictive these different attributes actually are. Let's see. There's one. I think there might be one other thing. Okay, yeah, biases. I skipped this one. And then this is basically the last kind of thing before we go back into just like a little bit more of the coding stuff. Okay, so statistical bias. This is, where the expected value, which is itself a kind of a piece of jargon. The expected value of the results differs from the true underlying parameter being estimated. So this picture kind of does a good example. So let's say this is the what's in gray, is, I guess, like the true north, right? Like these are the people who are going to be voting, and then this is and like this is kind of the way they feel, or this is how they indicate that they're going to be voting. So if we have low bias and low variance, we're getting all the individuals, and we are trying directly in there. If we have bias, right here, you have high bias and low variance. We're consistently off in the population. This is, for example, the study that's only assessing, the male animals, right? It doesn't matter how large a population we get. If we're only sampling male individuals, and those individuals are different than female, right, in terms of medical attributes, whatever they're assessing, right? It doesn't matter. We can increase it to 10,000. We're still not taking a sampling of the underlying population. Variance is the fact that, if you just sample one person, like obviously how many conclusions are you going to draw from that person, or three people, about the entire U.S. voting population, or, how often they go to the gym or whatever. So variance can be solved by taking a larger and larger, proportion, as long as your technique is not biased, right? Once you increase this to, generally over 100 for many studies, 1,000 is fine. You are good. The whole problem is actually bias, right? Because bias cannot. It doesn't matter how large the sampling is. It's going to be off. All right. So that's the point of going through this. So different kinds of biases that can occur. One is, selection bias, and this is with the sampling frame. So if the sampling frame is not representative of the population, then you're going to have, or the sampling technique is not, right, then you're going to have selection bias. So this is going to come with, we call people from a phone book, but not everyone is listed in the phone book who's going to be voting, right? We call it, then comes into that's the sampling frame. The sampling technique is we call them. Not everyone who picks up the phone is going to be necessarily represented. Random selection, I said, this is kind of fine. This is a key one. This is like kind of the key one, I'd say, that always comes up is non-response bias, right? Non-response bias, statisticians try to control for this all the time, meaning that, someone's not picking up the phone. Cool. What do? If they randomly select that person from the phone book, again, the ideal is a simple random sample. So they're going to recall that same individual many times to try to get them to answer. The reason why they pay that person is because they want to decrease their non-response bias. The reason for this is because there are many reasons for someone, not being there, not picking up the phone, not wanting to participate, and these are oftentimes correlated with attributes of the underlying population that are predictive of your results. For an example, people who do not pick up the phone may be poorer than people who do. Why? Because they might be working, more often. They may, as we saw in the 2016 election, right? They may not, trust kind of surveyors, right? Or which correlates to just not trusting institutions, which highly correlates to, their political beliefs, right? So non-response bias is kind of like one of the main biases that people try to control for, and this is when we chose our sampling frame, we randomly selected this person, we tried to enroll them in the study, and then they just simply don't want to participate or they're unavailable, right? And this is just very highly correlated, oftentimes, with what you're trying to predict. And then again, there's dropout. Right? People that, hey, I just don't have time for this. I don't really care about your $10. I'm dropping out of the study. And then reporting bias, this is like even after we collect the information, say you ask the person who are they going to vote for, and they lie to you, right? This is the poll booth kind of thing. Like, they don't want to say they're not going to vote for this person. They think it's cool to say they're going to vote for this person or whatever. But then when it comes down to it, they don't, or they just want to lie to the person, or it's just like people misestimate, or that's not a word, but people don't accurately recount how often they go to the gym, how often they read a book, right? All those things. So people try to correct for this. In studies, what they'll do, right? They can look at the actual gym logs, right? As opposed to ask someone how often they go to the gym. For like American Time Use Survey, what they'll do is they'll like have like beepers and kind of ask people, at this moment, what are you doing? Write down what you're doing right now, as opposed to what did you do last week, right? Because of reporting bias. And then, of course, there's juking the stats. So this is, of course, very, very popular, which is the moment you try to measure anything, and then we know that you're going to assess us on that, right? People are going to try to game the system. Right, you have all taken exams, so you know that you'll study the night before the exam, or of course, like schools do this as well all the time, right? They try to teach the test. I used to get pretzels and juice the day of the exam to try to boost our scores and make us more attentive or whatever. So these are just all the different things that can go wrong. So again, the reason why we go through this, I think this checking a data set, reading does a good job, and then this will kind of be the end, is let's say you get a data set on, NBA players. Sorry for keep using like the NBA. But like we get a data set for the NBA. Oftentimes what I'll see people do is they'll just like check like the pdf.isna.sum, and it's like, oh, cool. Like we have, so players df.isna, right? They'll like calculate all the missing value, and say like, great, like these are the amount of NA values we have. And that's me checking for missing data. But think about like everything we just learned, the underlying population here. Like, what is that? It's NBA players? But is it, you should think about that. Is it NBA players who have played in X number of games, right? And then the way to see, like, is my data set complete and can I draw conclusions about it, isn't just by checking is NA, but rather trying to see, like, well, how many players are there that play in the NBA? Like, how hard is it to really calculate that? You find out the number of players per team, you find out the number of teams, and you multiply, right? And then we say we find out that there's like 500, then you see how large is the actual data set, right? So the whole point of this is when you do your analysis, you can't just start with the data set itself. Like the world doesn't start with your data set. There's the underlying world that your data set's trying to represent, right? And the way the data was collected and the is going to be inaccurate, and therefore your data set's going to be incomplete. And so what you need to do is kind of see, like, does your data set match the underlying state of the world? So that's what I'm doing here, right? I'm saying, hey, okay, we get 17 players per team. There's 30 teams, right? This is the size of my data set. This is the completeness, right, of my data set. And this only doesn't include, right, the people that entered and left teams probably during that time, right? Ideally, this should be probably a larger number because people, enter the NBA, they get injured, etc. But this is the kind of where, we're going to go more extensively into this. But this is the whole point, is like you can't just start with the data set and look at that. You have to be considering what does this actually represent underneath? What is the underlying population? And how do I check completeness based on that? All right, end of speech. All right, so these, we have these readings, and then I have this SAT data prompt. So this is using, I think, basically the same data set that you saw in the last class. But hold on. I didn't want to give. Okay. Yes. So I ask you to, I do some cleaning up for you, right? And what I ask you to do, after you do these readings, is kind of like look for missing data, right? So the first thing to know about with something like this is, well, what are we probably trying to predict? Okay, so let's say we're trying to predict or try to assess like college readiness. Let's say, and we say that the SAT is a proxy for it. Obviously, there can be issues with even that statement, but let's say the SAT score is a proxy for it. Now, one thing that you may try to assess is, okay, how well are individual boroughs doing, right? How well are individual schools doing? And for something like that, once we get to like this grouping issue, right, now you need to care about like the completeness of the data, okay? Like, why do we care? This might just be step one in any analysis, right? Because if we're able to even have like complete data, then maybe we can see what is, Brooklyn doing that Manhattan is not. What is if we have a completeness of the data for a particular school, what is this school doing that something else, that another school is not? But again, it starts with this step one of assessing, do we even have complete data to tell us what is the math average of a school, the math SAT average of a school of a particular, borough in New York, or like of New York City in general, right? So again, it starts with this first step of like, what is the completeness of the data? Okay. All right. So I'll let you read through these lessons. Do read through these. Take some time for in this defining a population of reading. Some people had, I thought pretty good questions about it. This is the whole issue about, okay, like what is the average class size in a college? And I think it's true. Like the average class size is just the number of classes there are divided by, the size. But the issue is when you're asking the question, like what's your intention behind it? And probably your intention is, well, if I walk into a classroom, how many other students are likely to be in the class? Okay? And the problem is that you're not equally likely to walk into each classroom or to be assigned to each classroom, right? They're very different size classes. Okay? So you can see like you're much more likely to be assigned or to be in the psychology, the U.S. history classes and public policy than the others. So you can't just treat them all as if they're equal, which is what happens if you just simply add them all up, right, and divide by the number. So the whole issue here, kind of with grouping, is when the groups are of different sizes, and then but you don't kind of account for that, and instead you give them all the same weight. You can really see this if you just have like two groups. It becomes kind of obvious, right? If you just to give like an example, let's say we have like an NBA basketball season, okay, and we have a player one, and he plays 40 games the first half, and let's say he scores like 25 points per game, per game. And then he plays, 10 games the second half, right? And he scores like 10 points per game. Obviously, like we kind of all know this, right? This is the number of games. Right? You cannot just add them up. Do, 25 plus 10 divided by 2, right? Like that doesn't work to say what's his points per game for the entire season. Instead, what you have to do is weigh them by kind of the amount. So it'd be, the way that you can do this, if you want to calculate this, you can say, okay, well, these were 80% of the games, right? It's 40 divided by 50. So it's 40 divided by 50, or another way of putting that is 0.8, times by 25 points per game, plus 0.2 times by 10 points per game. And that's kind of that's the result here. So this is the weighted average. And the way weighted average works is you multiply each event, or the value in each event. It's really the expected value. Expected value. Each event by the likelihood the event occurs. Okay? So the expected value in the first half is 25 points per game, and the likelihood it occurs out of total, right, is 80%. And then you take the 20, the other part, this is likelihood, or the percentage of the second of a game in the second half is 20%, times by the expected value, right? The average across those games is 10%, is 10 points per game. And that gives you the results. It's the same thing here, right? The likelihood isn't divided by each of these classes equally. It's weighted, right? So you can just take the percentage, the 15, and divide it by the total. This whole, and then take the 12 divided by the total. And then you say the percentage of being in an English class times by the size of the class when you're in there, plus the percentage of the likelihood of being in the history class times by the size of the class when you're in there. And the problem is the likelihood you're in the psychology class, US history class, right? This is much more significant, and the expected value is much higher, right? Which is why, the class size is going to be much higher. This whole thing is called like Simpson's paradox, right? It happens all the time. So just to give, I'm sorry to belabor this, but this happens just like will happen like even in the next lab. So this issue is, right, like here's another example, the Berkeley gender bias. Basically they found that men were much more likely to be admitted than women, and the difference was so large it was unlikely to be due to chance, right? But what they also found was the men and women were applying to different departments, and that the departments that women were applying to, such as like English, were less competitive than those with higher rates of admissions like engineering. Okay, so once you look underneath, right, like you can really see, you want to account for those differences. Really, what would be better would be to see the percentage of women applying to English department and the men applying to English department, and see if there's a difference, in the admissions rate there, right? So that's what they do here, right? They control for it for a department, and then here you can see, right, it's more similar. 60, actually, women have higher in this one. Okay. So that's the issue is grouping. So then the question, that came up was like, well, how much group, what do we really do about something like this? And the answer is you want to go down to a more atomic unit. Just think like, is there a more atomic unit kind of underneath this? Meaning like, for example, for going back to the classroom, it was seats, was like the more atomic unit, down to, the NBA players, maybe it's minutes per game, right? Would be like a more atomic unit, right? But like there's just other factors. And then it's, if you're kind of calculating the points per game, basically what you're asking is, or if it's points per game, are all those games weighted equally, right? Or should we be counting them all the same? Well, maybe not if you're playing, more minutes per one than the other. And then if you choose minutes, are all those minutes weighted equally? And I gave the example in a breakout room of like, well, maybe not if like some minutes towards the end of the game in a close game are worth more, right? Or are just different than those like normal minutes, or minutes, say, where it's a blowout. Right, and people do kind of just create different statistics, and like how deeply, like how much time should you really spend considering all this? One thing to know is like, oftentimes you can just test it a little bit, like test just getting the statistics for say a single game or two games, and then see how different the results are, and are they more accurate than the baseline, right? So you don't have to, like, I'm not proposing you kind of see every flaw and then go like nuts and get all the data for every little aspect, but assessing it a little bit and seeing how much is gathering a little bit more data, or checking this just, for say 10 examples, or just put it another way, for 10 minutes, for 20 minutes to check it out, that's probably worth it, right? That can be very, very worth it. All right, let's go to this example of the school stuff. So you can see we collect the data. We have this Barrow thing. Like, I didn't really know how all these corresponded to, so I had to Google it. But you can see kind of how they correspond. I don't like working with like these abbreviations because it's hard for me to know, to remember what do they each correspond to. So I recommend, replacing them with the actual Barrow. If you do that, let's see. We get these averages. We can see differences in the averages. One thing just to look at, they are kind of within range, it seems like, although Staten Island and Bronx, right here's like kind of a significant difference. You might just like kind of spot check this and see, do these seem fairly accurate? Just kind of, you just want to use your own intuition at a certain extent, or Google it. But that's like when you're looking at the data, just try to see like, okay, does this kind of make sense? Which we can talk about just doing that part, this is-NA thing, and how to handle that in a second. For right now, the first thing I did was just see like, do we have comprehensive data? So one thing I looked at and I noticed, when I did a value counts on the Barrow, and I saw Staten Island only had 10, and I was like, okay, so maybe we're missing a lot of data from Staten Island, and maybe that explains why their averages are higher than everyone else's, right? It could be that only the better schools are reporting. But then I think I Googled, and it says there's only 27 high schools in Staten Island, where there's 280 in Brooklyn. So there is going to be, so just Googling a little bit, only takes a second, can kind of tell you yes or no on a hypothesis, right? Or so we could probably look at the percentages of how many actual schools are there, and then what percentage of them do we have in our data set. The other kind of big grouping, so one grouping we're doing is like this neighborhood thing. The other big grouping that I think a lot of you kind of saw or looked at was the total students versus the number of test takers. So this is kind of interesting, right? Because it could be a few things going on. So one thing is, let's say we have 100 people in their junior year ready to take the SAT, but and there's 100 people in the junior year class, only 20 of them are taking the SATs, right? That's we have this non-response bias, right? Where the people that are taking the SATs probably look very, very different than people who are not, right? They're more probably doing more college prep. They're probably wealthier because they can, it's going to just correlate with, ambition or ability to go to college and afford it, right? So like that's going to differ a lot. So one thing I did was I started to, create this column of the percentage takers, right, for each school. So I just selected the number of test takers, the number of students, right, divided the two, and then added this as a column, okay? Now, you can look at this, right? So the next thing I did was sort the values by the percentage of test takers, and you can do ascending true or descending true. Because one question I had was, as you can see, only 4% are in this school in Manhattan, the Independence High School. West Bronx Academy for the Future has, and even if you do like the mean, it's only 14%, 15%, 16%. So one question might be, what is this total students? Is this total students per grade, or is this total students across the school? How would you figure this out, right? Like it's pretty easy, I think, to throw up your hands. But like I said, you only have to, to actually answer these questions, you normally just have to do like a little bit of Googling, and I'm not saying do it for every example. Just do it for a couple. So you take West Bronx Academy for the Future, you plug it in. You see I already did this. I plugged in class size. Okay, and then I just clicked on the first link. I did find it. It's hard for me to find it now. Class size, let me see if I can find it. Class size. So, here we go. The student population is 663, and the school serves grades 606 through 12. So now if you go back here and you look at the total students, 607. So it seems like, right, the 607 describes the entire class population, right? The other thing to kind of be curious about is, all right, well, this is 6 through 12. Even if I divide, so I can't just divide by 4 for every class to get an estimate, because some of them have, includes, it seems like probably include more classes than the others. So actually this percentage taking, like here, so if we divide it by 6, right, it's going to be boosted up to now like 24%. I mean, if we just do a flat kind of a quick and dirty guess on this, right? The point is, it boosts the percentage that are taking it up by a significant amount. I'm trying to find that number. So right, if only our class size is 1/6, right, then that will boost us up by 24%. Still not great, but shows you, right, the variant that you can't really rely on this perhaps. So that's kind of interesting, right? It's like, how do we get one thing to do? What would you do next? One thing to do is maybe get the class size for each school for each year, right? This number still seems low. Another question would be, you could literally call up the school and just, call 10 schools and ask the guidance counselor, like, does this seem fairly accurate, that 24% or something like that, or look for like another resource. But just like some initial Googling can do that. The other thing to do is maybe you can just Google in general, like what percentage of students in New York take the SATs, and see if those numbers start to line up, see if they kind of seem pretty accurate. When you're doing this I think what I'm saying is, like, when you're doing these kinds of analyses, it's good to check sources outside of your data set to get a sense of how accurate the data is. And you can do that without even, talking to people. And the reason why I recommend that is, you want to show that you've done some upfront work before you ask the question, because the people that are answering you might be giving you inaccurate information. So doing your own research just a little bit, only for like 10 minutes, can really help, right, and give you an understanding of the data set. All right. So we do have this problem, it seems like, even though maybe we're getting a higher percentage than this analysis calculates. If it's still only 24-30% of test takers, how do you work with this? One thing you could do, if you do like the descending true, ascending equals false. That's what I should do. Ascending equals false. You can see that there are some schools that have a pretty high percent. Like this is very high too. If this is a school that has, we can kind of figure out how many students there are per grade. There might be some schools, even if we can't work with the entire data set, maybe there are some schools where we can get a good sense, because the percentage is so high, of what the actual SAT school, score is. If that's the case, even if we only have, say, a few schools that have this information, say there's 10 of them, right? We can still kind of look at them and see, okay, what's different here? Information, focus on them is what I would do, right? Like, what can explain some of the differences here? Basically the factors are student body coming in, right? The education that's being taught, things like that. Those are probably the main one. You guys can probably brainstorm some others. Test prep type stuff, and then see, like, what are the different levers that you can potentially pull on to increase these scores, if that's in fact something you want to do. All right. So the point here is, like, even if it feels like this data set is too poor to work with, that might not be true, right? Like, if we have like 10 examples, that represents like 2,000 students, or probably more than that you can then just work with that percentage of the data, or that subset of the data, and conduct your analysis from there. All right, that's what I would advocate for. The other thing, of course, is if you look, I don't think you guys could have really looked at when this data is taken from. It's from like 2010, so you need more up-to-date data probably than something like this. But that's just another thing to consider. The other thing I did was, You want to just look at the data. Why do you want to just look at the data? You want to see that the data makes sense in terms of the range. Like, make sure there's no negative values that you're taking the average of. Making sure that there's no data outside of what's possible. Like the highest score is an 800. You want to make sure that's not, nothing outside of there is occurring. Right. So I talked about this, the timing, that missing data. You can still work with some information. Okay, the is NA stuff. People are asking, how do you handle this? So I just did, if you look at this, this is our data set. If you do the dot is NA, that gives a true or false value, which in Python, true or false corresponds to 0 or 1. And then you can add them up, right? So you can see we have all, one, you should know this is not sufficient for seeing, do we have a complete data set, right? We already saw that we're missing 17 schools in Staten Island, right? But how would you handle this data? Like, one thing, the easy thing to do is just throw out the row. But something that could be, that's kind of like better than that is for the information you're trying to predict, it is hard to work with it. So in this example, something like the reading average, the math average, the writing score, it's very hard to work with that data because this is what we're trying to predict itself. So, it's hard to see if more schooling or more hours in the classroom corresponds to a better math average when we don't know what that math average is. However, so this is, filling in the target information. That's really hard to do. Oftentimes you do just throw out that data, meaning you throw out the entire row where it's missing. However, if it's feature data, right? Feature data. So let's say we have a column of number of classroom hours. And let's say sometimes it's NA, it's missing. Normally what you'll do, and other times it's present, so it's 100, which seems small. Let's say it's 1,000. So what you'll do oftentimes is you'll create a new column called is number classroom hours NA, okay? Because the missingness itself is information, okay? We just saw that we know this because of non-response bias, right? We know that the missingness is itself kind of like information in itself. So you can now pass this feature into your machine learning model or any kind of statistical analysis. And then here, oftentimes, at least for ML, you'll replace this with the mean, with the average. The reason for that, let's say here we have a true. This will be false, and here we have 800. So you'll replace this with the average, which would be 900. The reason for doing that is the average has the least impact on your data, right? It's in the middle, so it's not going to sway it one way or the other. So for an ML model, you can't pass through missing values. So what you'll do is you replace this with the average, and then you'll have a new column that indicates whether or not this number is just the mean or not, right? So you're not losing any. You kind of can still track what's real or not. And the benefit of this is that, like I said, this can be very predictive. Knowing whether or not something was missing can be very predictive of an outcome. An example of this is, there's these data science competitions. Kaggle is a very famous one. And there actually was an admissions, kind of predicting whether someone would be admitted to a college. And it turned out that one feature, having information missing, the missingness was it was basically 90% predictive of whether the student was going to be admitted. The reason why was because, or whether they would be rejected. The reason why was because once they determined the student was going to be rejected, they just stopped filling out the information. So this was a trick, but like I said, you just don't know what's going to be indicative, what's going to be a valuable feature. So you want to hold on to this indication itself. So this is the typical way that you handle missing data, is when it's a feature, you can just replace it with the average and then create a new column indicating whether or not that data was missing, something like that. How do we check if there's bias in a data set? Okay, good question, Narapati. Okay, so things that you can do is, you can look at, you have to kind of make some assumption. Oftentimes, you can check it along the way, right? Seeing, how's the data collected, things like that, right? But oftentimes what you're doing is you're looking for, deviations in the data from what you know to be the underlying truth. So what would be an example of that? Right? We're doing it up front when we, one, are seeing what's the breakdown with the value counts, right? Because if we're seeing that like Staten Island, what's the response of Staten Island percentage, right, compared to Brooklyn, Manhattan, the Bronx, Queens, all the rest of them, right? Then chances are it's not just the fact that they're from Staten Island, but that Staten Island is different. Oftentimes, income correlates to everything. So oftentimes, if you see that okay, some subset of the data is not showing up, right? It's often biased, right? And like I said, it's often very highly correlated with wealth. Is just like kind of a go-to that you can kind of guess or then do further research on. So that's kind of one thing is you want to see like what is the truth or what can you figure out about the truth, and then check to see if those features line up. So that's why you do kind of these kinds of plots too. If you want to see, here we're doing the math and reading average in the aggregate, right? Like total, but we could do this across each borough as well. If we see that one borough is doing very, very poor or very, very high, right, other than what we would expect, you should evaluate that. Oftentimes, again, it's due to like missingness in the data, or misreporting or something like that. Sometimes not, right? Like I've heard there was like a classic case of like they believed that a school just made up their AP scores, and they had them redo it because it was too poor of a school, and they were wrong. There was just a excellent classroom. So, but that's right. What you would look at that's why you would look at like outliers. That's why you look at distributions in the data. Is basically you have some understanding or some hypothesis about what the ground truth looks at, and that's what this exploration is about. Is to see does it deviate from it either in the results, okay, or in the count or characteristics of the features, right? So that's part of why you do these kind of like counts thing. Right here was another case of us finding probably non-response bias or being very susceptible to it is the fact that even though our percentage of takers in most cases was maybe it was, even if it was higher than this, there's going to be a percentage of people who are not taking it. And so what are their results, and where is that most pronounced, and then how do we correct for it? Right? And one way of correcting for it is simply either one, collecting the data, or two, working with a smaller subset of the data set, which is kind of what I proposed, which was like find the highest quality, can we draw conclusions based on a smaller data set that we don't have an argument for it being biased, right? Or it seems less susceptible to being biased. That's normally my approach is like, oh, cool. We have data from all over the place. We have to throw out 80% of it, but we can work with, or maybe more than that, but we can work with 10% of high quality data, which still might be 1,000 examples of complete, observations, and that's what you can work with. Questions about this? We're going to do another example of this as a lab. So what was the techniques we did? One, we kind of looked at the dimensions of the data. For this, it wasn't a lot, right? It was the borough was essentially it. One way we could divide up the data. The year is typically another one, but we don't have the year, right? So you can just think of like how can you divide up the data? Then you can look at kind of like outliers in what you're trying to predict and make sure there's some sort of ground truth in them. We looked at any place that there were groups. An obvious one was this is an average, right? This is per school. So then if it's per school, what are we really trying to get at? It's like, well, what's the performance of the student body? The problem is we don't have the performance of the entire student body. We only have a percentage of it. So then what do we do with that? Well, perhaps we should just look at the schools where we have that higher percentage of answers, right, from the student body. That way, we don't have this non-response bias, at least across a subset of the schools. Okay, so like that's how I would approach this, at least. And then the other thing I would do is I'd try to get that number of classrooms and number of people per grade. At least try to like how many students graduate each year. as opposed to the total number of students, right? This is kind of throwing us off or not providing useful information. Cool. All right, questions about the next thing is going to be, I'll deploy the solution here, and then the next thing is going to be this checking a movies lab. And it'll be the same, right? Like it's the same type of thing. One, you want to analyze the data set, and two, ask some questions about if need be. Let's say we're working with this product data, right? And we have this product sales. Typically, what you'll see, right, with kind of any attribute is if say this is cumulative sales, is it'll look kind of like this, I guess, and then start to taper off. So you'll see like, this is the amount of MacBook Pros, and then, so say like 25% of our sales comes from MacBook Pros, and then another 20% comes from, iPhone, and then another whatever comes from 15, comes from Android, and then we get, another 10 or whatever comes from, TVs, some sort of TVs. Okay. 10. So, and then there's everything else, right? Everything else. So like just to tell people, hey, 80% of our data comes here, or 80% of our revenue, right, comes from here. Now all of a sudden, right, you know where to focus your attention. Like you can always, obviously, like just forgetting about 20% of your revenue, you don't want to do that either. But if you're starting, this is your first, 6 months, right here, they just hired their analytics person, this is still probably what you want to focus on every day, like a lot, right, is these components. And typically what you see, kind of like what we see with the 80-20 rule, is that 80% of the impact comes from like 20% of whatever it is, whether it's products, whether it's, stores, whether it's salespeople, whether it's customer, right? Like typically you'll see this kind of pattern, right? And, you'll see in the readings, which it just kind of, took random data sets, they tend to follow these patterns. So the first step is kind of know what to focus on. And to do that, it's like pick your target, which is like profit or revenue that you're trying to optimize, and then figure out what drives it. And again, like this can be across different dimensions. So here we're choosing, applying the 80-20 rule to products, but it could also be right to locations, right, to any kind of dimension of the data, whether it's products, time, right, the weeks in a year, it could be locations, right, it could be customers, right? And then kind of the next technique I recommend is one, kind of like what I typically do is just select those products and then see what drives sales of that product, or just select those relevant times, like those weeks that are really valuable, and then see what drives, perform another analysis of, those relevant times, right? Who are our most important customers, and then see, well, where do those customers live? What are they buying? When are they buying it, etc. Right? So you just basically select the most important components, those that are driving it, and then apply the exact same analysis, meaning perform a group by, see what's the 80-20 rule look like on these customers. Where do they live? When do they purchase, etc. What do they buy? Right? What's the 80-20 rule look like for these products? Where is it bought and sold, etc. Okay? So it's like you first start here with what's driving your revenue, and then you can go, deeper from there. The other thing is then, looking for surprises in the data. So for example, if you have a presentation that's like, this is your first week on the job, and they just hired their data analytics person, and you say, 20%, MacBook sales drive profits, accounting for 20% of our revenue. That's slide 1, and it shows something like this. Then slide 2 is, Seattle sells 40% of MacBooks, even though only 20% of our customers. Basically, what you're saying is let's go to Seattle, right? Let's figure out what's going on there. Is it their salespeople that are doing it differently? Is it the customers that are, kind of our core customers that we just don't even know about yet? You don't know, right? Like lots of times the data isn't going to tell you the whole story. But if you're able to, first of all, kind of focus you, right? Focus us on what's important, identify the drivers, whether it's, across whatever dimension it is, and then kind of tell us something, either it's, sometimes it's, all right, well, New York and, Chicago or whatever. And that's kind of typical. But if it's unexpected, either positively or negatively, right? That tells you something to do, take action with it, right? So it's like an actionable insight. These things should follow one another, right? If you're doing, and there's a reason why these are in sequence, right? Because if you're doing, okay, well, keychains, for whatever reason, 80% of keychains are sold in Tampa, but they only account for 1% of the revenue or whatever. Why are we focusing on that? Why do we care? So it's first, okay, this is really important. And then, kind of hey, look at this. You don't always find something interesting or surprising, but sometimes you do, or even kind of slightly surprising can really be noteworthy. So it could be, like I said, it could be in a positive direction, above. It could also be negative, right? It could be, hey, New York accounts for the opposite, right? Accounts for 40% of our customers, but only 20% of sales are there. What's going on, right? Why are they underperforming? So again, oftentimes what's happening with these, and it's still very powerful, is you're not necessarily this is why, but rather we should go look here. We should figure out what's going on. It could stop with the numbers at that point and be we need to get people on the phone. We need to go check out these stores for X amount of days and figure out what's going on. And that's enough to have a very meaningful report. In terms of, but these are the two techniques I'm recommending. Is one, kind of apply the 80-20 principle to identify what to focus on. And then two, when you do that, you can kind of select that data and then find surprising differences in the data. Okay. How do you do that? From with some code. Essentially what we're doing is just grouping the data, right? You can see that's what I'm doing. We load up the data. We perform a group by, meaning here we're grouping by the product, right? This is our dimension. We identify the target. We add them, right? We find the total amount. And then I just turn it into a percentage. What percentage of total revenue is this? So I just get this sum column, divide it by all of them, right? The sum of this entire column. And then say, okay, it is 23%. Then it's down to 13, then it's down to 12. And then if you do a cumulative percentage, right, instead of sum, here, take the sum and apply, the cumulative sum. So it's 23% plus 13. So this is 37%. And the benefit of that is it tells you when to stop, right? When have I reached 80% of my revenue here? Okay. So you can see I turn that into a function here, right? The aggregate is the sum, the target, right, is the revenue, the column that we're going to be grouping by, and then sort the values by that same sum, sort it descending, meaning from highest to lowest. And so now you can kind of see that this is pretty easy to do, and we can choose a different dimension. So here we're doing it by city, and we're saying, okay, you can basically stop. If we hit 30 cities, well, 70% of them, 70% of the sales are in these 5 cities. Now there could be, you can't forget about the danger of grouping, right? It doesn't mean that whether or not this is good or bad or as expected, we don't know yet, because it's well, how many stores are there per each city? like who, is our target market? How does that break down per city, right? It's not necessarily like super we can't conclude too much yet, but it's a start, right? And when you get these kind of nebulous problems, what I recommend doing is think about like, what is the target? Where are we trying to optimize for it? It's typically profit, right? And then from there, well, what are the different dimensions of the data, right? So just think about like the dimension of the world, right? Geography, time, right? And then with a business, it's going to be like these products. It could be more than just that. But and then you can think about other units, right? So if it's cities, what's a deeper unit? What's more atomic than that? Probably like the stores, the individual stores. What's more atomic than that? The individual salespeople, right? The customers, individual customers, things like that, right? So you can break it down and apply the same kind of analysis across that. And then you can see I gave you this print group by, right? So you can just kind of visually, easily see this. This is the percentage sales by city, but then there's the cumulative percentage. So it tells you again when to stop. Is Atlanta, Dallas, right around here. It's kind of like when you can stop looking and really just focus on like these cities. 3 cities account for 60% of the revenue. In terms of a number of you like asked, how do you use this, especially in the lab? What you can do is just in the code, do exclamation point touch item lib, shift return. Right, this will use the bash command. Oh, sorry, itemlib.py. I don't know what I'm doing. And then that will create a new file for you. Can I rename this? Yeah, itemlib.py. Ugh, that's wrong. There we go. And then just paste it in. Okay. So now we have these things. I can hopefully save it. All right. And then it didn't work. I think that's fine. And now let's see. We can do like from itemlib import star, right? So we're importing all the functions. And now, right, we have this add date part function, for example. So here's the order date. We have the data frame, and then we can add date part to the data frame, and the field names is order date. DF is not defined. I just didn't press shift return here. And I think this operates on the data frame. So now if we look at the data frame again, right, it will have the month. Oh, here it is. Order year, order month, order week, order day of week. All of a sudden we have a lot more features to break this stuff down by. Now they may feel a lot more work, but it's really not, right? Because you can just use this lib to quickly build and print by as many columns as you want. Just pass through the list of columns, take a look at it, and what you'll find is some of the columns will adhere more to this 80-20 rule than others, so you can kind of start there. And the other thing is, okay, we just, like I said, you can then, select all the MacBook Pros, or maybe, select 3 products and see where, just select them, and then select those rows that have a product of MacBook Pro, and then apply the same type of thing. Build group bys just on where we sold MacBook Pro, right, to see where are those sales occurring. Why is something like that also valuable? Well, if you're selling, electronics, then it's probably, and that's what's driving your business, it's probably good then to figure out, learn more about kind of your electronics customers. Where do they live? Who are, the successful salespeople? What does that look like, right? So, you can kind of start with like your kind of core part of your business and learn more about that, and, learn where it's being sold and when, etc. It tells you what to optimize for and what to focus on. And again, you can look at things that are unexpected in the data, meaning, if if you then look at MacBook Pros and you see, hey, you're not selling this well, like around, Black Friday and that period, it's like, why not? You need to identify why you're not selling it too well, what's going on there, whether it's discounts or advertising, et cetera, et cetera. So that's kind of like, the approach that I recommend. You first need to do this whole, is the data representative? It doesn't help if you think that you're selling MacBook Pros really well, but the data is actually 10 years old, right? That's not going to work. So you first can, explore the data, that, select the relevant, make sure it's representative. You can see that part of that is, this doesn't illustrate it super well, but looking at it per month, per week, right? A lot of these data sets, what you'll find is they're not comprehensive in terms of the time period. So if you do a yearly sales, but it stops in June, right? That's going to change a lot of your numbers, and it's just very obvious that you didn't look at the data too well. Here you can see that occurred, I think, right? So we have revenue. I think there's like a certain percentage. It's like all of year 2019, and then only a portion of 2020 or something like that. So if you just kind of get a sense of how comprehensive or representative is this data to begin with, then where do I scope kind of my data set, if need be, to get that representative portion, and then apply the 80-20 rule. From there, you can select the portion of the data that drives, your revenue or your profits, and look for surprising differences or surprising components of the data, right? And the way to do that is you just simply select, MacBook Pro, iPhone, ThinkPad, whatever, and then see where are those sales, when are those sales, et cetera, et cetera. Kind of just apply the same thing, right? So this is what I'm saying here. Select a subset of the data. Here I'm selecting where the product is MacBook Pro. I'm comparing that, to see surprising differences in the data, I compare that to where the product is not MacBook Pro. So maybe like MacBook users operate differently. And then what do? I just take the MacBook sales and I call that same build and print function on, the city, the order month, the order week. I could have chosen more, but like if this is so important, where are they sold? When are they sold? And you can start to see that. And now, how does that differ from my non-MacBook sales, right? Because this would tell me, because if it's like, oh, well, all your sales are in New York. Well, great, of MacBooks. Well, all my sales of everything are in New York. Like that's not interesting. It's interesting if all the sales are in New York, and New York's actually not a big city for us, because maybe that means we should have more of a presence in New York. Okay. Here I do, this is hard for me to remember, but of like how to implement this, but here I do like a multi-level group by, right? It's like MacBook sales in San Francisco, right? It's basically, grouping by 2 columns account for 5. And this is the biggest breakdown across these 2 columns, is 5% in San Francisco, 3% in Los Angeles, right? So it's like, if you're going to go to a store to any kind of region and one kind of product, I guess this is the combination to focus on. But just those 2 earlier approaches are quite good, I think. When would you use Pandas for data analysis versus a BI tool? This is a really good question. So when would you use Pandas for analysis versus like Tableau? You start off, my view, and I've talked to with data analysts as well, you start off with Pandas, right? And figure out what's significant. Like, the BI tool is basically building dashboards. But it takes work to like make a nice dashboard and clean it and decide, hey, this is what we should show to people. It's a lot easier to, kind of try this and then try that and explore the data, see what drives the revenue first. Some of these charts are not going to be interesting, right? So we first quickly do it with plot them with pandas, and then you see what are the interesting charts, meaning, where are the unexpected kind of differences, what's the level of granularity that's important, right? Is it weekly, is it daily, is it monthly, is it city, is it per store, right? What's the cutoff, right? So you first explore it and figure out the important charts in pandas, and then you can turn that into a dashboard in Tableau or something else. Okay. The other thing is, right, you have to clean the data, you have to choose the right subset of the data. Like there's real engineering work first, or at least, pandas work before doing that. So this is the approach, right? Like 80-20 analysis, because you're going to start just with a data set, identify your target, do group bys basically on every column you can. First, right, do the add date part. That will add features, right? Add the breakdown of a single date column into, day, week, et cetera, et cetera. Then find the drivers across different dimensions, and then see what's kind of surprising differences in the data, right? Whether it's when it's being sold, by whom, the region, right? And again, lots of times you're not concluding anything. It's not like San Francisco, so that means we need to expand stores in San Francisco. We don't know that. It's more, let's look into this, right? Normally it's a lot more research and a lot more non-data research, right? Not quantitative data research before you conclude any kind of action. But, just saying we should look into this a lot more deeply, that's a success if you're able to convince people of that. Right, and then for the building a library, like I said, you can get that in I put a link to it in Slack, but also it's just what's at the very bottom here of this thing. You can just copy and paste this into a file and create a new file with touch itemlib.py. All right. So for the exploring a data set for the lab I give, a lot of it is going to be printing this, and then of the plots, which one of them are interesting, and then what do the plots kind of indicate that you should look more deeply at, right? How do we scope down this problem to decide where we should devote our focus? Okay. How do you all feel about this? Okay, great. Cool. Because I think that's the heart. I did put a link to the Kaggle. So it is a good idea to just read the description to know what you're dealing with. And I guess one thing, so it says, okay, ranking of overall sales, the game's name, year is the year of the game's release, total worldwide sales in millions. The thing that I would think I had to pay most amount of attention to was the year of the game's release. The reason why is because so the year of the game's release, games released a long time ago, probably not too relevant, right? The trends may change. This was my big question, which I guess we'd have to do more digging to figure out, is the sales in the aggregate, is this total money earned since 1985? I kind of think it might be. If you see Super Mario, and maybe I'm wrong, but if Super Mario Brothers, which was released in 1985, this is the amount of sales, it ranks number 2. It just doesn't seem right. So, my solution was, okay, and we kind of look at the range of data. It goes up to 2020. So that's probably when this data is from, right? Is right around then. So then and then if you plot a histogram of this, you can see though that, if we look at, sales since 2020, you see that we hardly have any representations of the data, right? This is 50. So if you plot a histogram, you can see 2017 really through 2020 that we have 1-2 examples, and that's it. So you're not really going to draw any conclusions about what's popular in 2020 based on 1 or 2 examples. It just seems like we're not capturing data from there. And then we have, we want more recent data. So what I did was I was all right, let's just select data between 2009 and cut it off at 2016 and take a look at that and see if we have some representative recent data. You can see it still is skewed, right? Like this is representing more. So if you want to get, if we're gonna like assess this in the aggregate, like what is driving sales, maybe we shouldn't consider like maybe we could, and I think this is debatable, but what I did at least here was say like, all right, let's lop off this, older data that, I don't want to draw conclusions about things that are further in the past and then maybe like skewing it, right? It might not, say there was lots of like, sports games here, but I don't want these things to drive my analysis if it's not kind of true over here. So, I decided to cut it off here where there's more of an even distribution and it's also more recent. So you can see I'm like, okay, only select the data after 2011, right? And we still have pretty good number of examples, right? It's like 600. Like it's still pretty good size of the data set. You do see that it cuts down here, which pretty significantly by half, right? So this is also something to look at. Maybe this is, I don't know why, honestly, but it's something to consider. Like why is this so much less than the other ones? But you can see that just already scoping down the data is going to change like the rest of your analysis, right? So you want to justify it and kind of decide like what are you trying to draw conclusions of if you're trying to predict like what's going to be like star video game, right? Like choose, obviously data probably from 1985 is not super relevant. So that's kind of the next thing. Then from there, it's, choosing a target. You can see here as well, it's like you have these different possibilities: North American sales, European, Japanese, right? Like, or global. So this obviously is all inclusive, but maybe you just want to focus on North American. Maybe these are predictors. In other words, like features, like maybe like, for instance, European sales, is that like a leading indicator of like first action games do well over there? And then, that's an indicator of what's to come in the US. Like, I don't know. And you can see basically what I just do is like try to see, is there some sort of 80-20 analysis I can, provide. And I just do it basically based on a lot of different characteristics and go from there. And you can then do a deeper dive. So let's say if like, there's maybe something interesting here. Like I'm not a big gamer, so I just don't know Activision and Ubisoft. But maybe it would be worth like, maybe this is something surprising that then you would take a look at and see what they did if they're like this rising star. Yeah, so we're basically out of time. But I did want to show you, I know not everyone got to hear, but I think this is the part I wanted to emphasize, was just up front. You can really show your stuff, I think, in an analysis and just have a big impact on the rest of the way you do analysis by just figuring out like what's relevant, what's going to be kind of what do we have a fairly comprehensive sample of that then we can draw conclusions about and then go from there and just apply the 80-20 rule. In the next class, we'll probably do like a little bit more analysis. I do want to get